All right, Isaac, I am ready whenever you are.
Okay, let's go ahead
All
and
right,
get started.
Isaac Greenspan, here we go.
My apologies for comparing you to Fox News with the first title there. I want to talk about some of the things that we tell students that aren't quite true, but that are true in the moment. We tell kids they can't subtract bigger numbers from smaller numbers. We tell kids they can't divide 10 by 3. Well, then we tell them they can, but you get a remainder. Then we tell them that it's 10/3 or other things. We tell kids they can't take the square root of negative numbers. We tell students a lot of lies, and pre-calculus is a particularly good time to stop lying about things. Maybe it's a little late. But at pre-calculus, we're at a point where we can give kids a complete picture, where there aren't loose ends floating around. And the key ideas I want to hit on are the idea of sets that are closed, sets that have identity elements and sets that have inverse elements. That's a lot of fancy words for saying we do operations and we stay within the numbers that we have. I want to go back to the beginning and start with counting. One, counting numbers are the numbers we start with. I'm going to give a formal definition of counting numbers based on the piano postulates. We start with 0, and there's some convenience and some history to that, but it could be 1. I'll start with 0. 0 is a natural number. For any natural number, the one after it is also a natural number. If we add 1, if we take the successor to that number, we get another natural number. There's no number that comes before 0 in the natural numbers. And if the next number of two different numbers is the same, well, those were the same number. If we have m and n and the successor to m and n are the same, then m and n are the same. And this last one is the induction principle, except that should say n is a subset of s. If 0 is in the set and all the successors to any number in the set is in the set, then the natural numbers are in that set. That's a formal definition for the natural numbers. We can also do them geometrically. If we have a point that we call 0, and we have a vector from 0 to 1, a way to translate from 0 to another point that's 1, we can then translate 1 and get to the next point, and 2 and get to the next point, and 3 and get to the next point, and we can construct geometrically the natural numbers that way. The natural numbers are closed under addition. If we add any two natural numbers, we get a natural number. If we multiply any two natural numbers, we get a natural number. We have an additive identity element. We can add 0 and we get the same number. We have the multiplicative identity element, 1. We can multiply and get the same number. But they're not closed under subtraction, and they're not closed under division. So let's fix subtraction first. If we have the natural numbers and their opposites, the reflection image of all those points across 0, which is also geometrically constructible, then we get closure under subtraction, and we get the integers. So now we have closure under addition, closure under subtraction, closure under multiplication. We still have our multiplicative and additive identity elements. So we've got more operations that we can do now than we could before, but we still can't divide. If we look at ratios of integers, at dividing integers, at scale factors, at multiplying, dilating, geometrically dilating is constructible, we get the rational numbers. Now we're closed under addition, subtraction, multiplication, and division. We finally filled in all the holes in arithmetic that we had from the beginning with the natural numbers. And that's a nice set because it's closed under those 4 operations. But what if we look at sequences of rational numbers? 3, 3.1, 3.14, 3.141, and so on. If we have sequences that converge, and I would say Cauchy sequences, the limits of those give us the real numbers. Any sequence of real numbers that converges to a real number. Any sequence of rational numbers that converges might converge to a rational number, but definitely converges to a real number. So the real numbers are closed under limits. Taking the square roots of negative numbers is the one thing from the beginning that's left over. If we do that, if we take the square roots of negative numbers, we get the complex numbers, which are now algebraically complete. They're algebraically closed. Any polynomial with real coefficients has a solution in the complex numbers. Any polynomial with complex coefficients has a solution in the complex numbers. but we're still lying. We can do a little bit more than that, and this is always the point at which my kids would say, well, okay, so now we know how to take the square roots of negative numbers. What else are you not telling us now that some teacher is going to tell us in 5 years we can do? Compactification points at infinity is one of them. Hamilton's quaternions is another. The notes will be at that URL. There's a draft up there now, and there's my email address. Thank you.